So yeah, it's like.
Okay, so thank you very much to the organizer to invite me to discuss about my work. So it's a joint work with my PhD student, Maxence Noble, okay, and a former PhD, Valentin de Bortoli. And okay, it will be, in fact, okay, so the talk is named about okay, the algorithm that we proposed and analyzed, which we named Self-Concor by HMC, and I think a lot of you know about HMC, but here, in fact, what we want in a nutshell is to define properly, in fact, an HMC algorithm on some constraint space. Okay. So just, I will start with motivation and a bit of a background, okay, the tools that I will use during these talks, okay. Then, okay, we'll go properly to the methods that we suggested and analyzed, and we go to the numerical experiments and hopefully, in fact, to the conclusion. Okay, so here what the problem that I want to handle is, okay, here I'm given a subset M on RD, right? And I want to sample from a probability distribution pi, which is supposed to have a density with respect to the Lebesgue measure, okay? Proportional to exponential minus V. And V is the usual potential function. And here I will not motivate this problem, okay, that you want to sample from pi. Okay. Everyone here, in fact, is motivated about this problem. And okay, so here, what is the motivation that I want to, the problem that I want to face on is that to consider the case where M, right, is not necessarily RD. Okay. So here is what we, the problem that we want to handle is the problem what is named the constraint sampling, okay? And here, okay, the density it is quite badly written, in fact. Now I realize it. Here, in fact, you should have somehow the indicator function of M. So in the case of the constraint sampling, okay, in particular, if the geometry of your constraint space has some sharp angle, or in fact, if the geometry underlying, in fact, the potential itself, even if you are on RD, is quite complex, okay? That's an usual MCMC algorithm, and gradient-based MCMC algorithm can struggle, okay, because you are in general what is called not very well conditioned. And okay, when you, so here, in fact, I just plot here, this experiment are some from paper by Alain and M.Carl head, where in fact, you can see that here is just the traditional Hamiltonian Monte Carlo algorithm, where in fact you struggle from exit from this corner, right? And what they suggest is somehow to incorporate in the HMC algorithm the geometry of the potential, okay, to guide the proposal and to in fact exit quickly the angle there. So that's basically the idea which is in the paper of Alain and M.Carl, but in fact there is a lot of work even beside in fact this work which try in fact to use adaptive MCMC to try to adapt proposal to the geometry of given targets or under some constraints. So here, in fact, just to and then okay so here it's in the case where you can incorporate some additional information of the targets. In fact, what's the main idea of Girolami and Calderon? That's in fact you will incorporate the extra information about the target by in fact considering a metric, okay, on your space, which is somehow in fact designed to handle this the potential that you want to sample from. Another, in fact, so here it's a first idea, and here the second idea that we want to consider is that here we don't want necessarily M, okay, to be RD, okay, and to handle, in fact, constraints, right? So here I will consider some constraints which can written on the form C of X equals 0. So here, in fact, my constraint space is just 0 of a given function. Okay, it's not the most general form, but okay, it's in application you need to face this kind of constraints a lot. And for this, okay, you have already, in fact, HMC algorithm kind method, which in fact handle these constraints in such a way that in fact you somehow adapt the traditional HMC algorithm to handle these constraints. So now, in fact, the main idea that we wanted to have is, can we in fact try to combine both ideas? Okay, so here, in fact, we want to first take advantages that's okay. You maybe you know extra information about M, right? And also that M is really, in fact, it can be written as a 0 of a function, or even, in fact, have or in fact inequality constraints. So here, in fact, the main idea that's what's the method that we want to we propose is try, in fact, to consider the state space, okay, a state space which is defined by some constraints, and put here some metric in such a way that the even complex geometry of M, in fact, can be handled by some appropriate metric. So what is a metric? Okay, so here just a bit of so here it's a quick introduction about this notion. So I will not give you a full course about it, but just in fact to give you in fact the intuition and the idea how in fact HMC can be extended to Riemannian spaces. So here, so I would consider M so a manifold, so a constraint manifold, and here G, a metric, is just in fact a smooth vector field which is defined on the tangent space of my space, meaning that okay, the tangent space is all the direction that you can follow infinitesimally and still end up in the manifold. Okay. And based on the tangent space, you can define the cotangent space. Okay. And that's in fact why in fact I want to introduce the cotangent space. Okay, it will be clear afterwards. But it's really how in fact to generalize HMC is much simpler to consider the cotangent space. And here, what is the cotangent space of my manifold is just the dual, okay, at a point X of my manifold is just the dual of my tangent space as X. And here, since I just handle with, let's say, D-dimensional manifold, I know that, okay, you can identify this set with RD, right? And here now, okay, if I start with metric on my manifold M, okay, now in fact I can. So what does it mean to be a metric? It means that okay, you have somehow a scalar product on any tangent space at every point of your manifold, and in fact this metric evolves smoothly across your manifold. And here now, okay, based on this metric, okay, so let's say canonical matrix, okay, on now your cotangent space, right, at a given point X, you can identify this time on RD as in fact this scalar product with in fact the definite positive matrix given by the inverse of the metric. Okay, so here in fact in general on the tangent space, the matrix, in fact, defines the scalar product as, in fact, the scalar product associated with the symmetric definite positive matrix G of X. This time, in fact, since you handle with a dual, you end up with the inverse of this matrix. So now, in fact, if this metric, this norm now here associated with the inverse of this matrix, in fact, with this particular norm now, in fact, the canonical Gaussian random variables, okay, at my given point x, in fact, can be identified this time, not as a standard Gaussian distribution, but in fact with a distribution, with a Gaussian distribution with zero mean, of course, but this time with the covariance matrix, which is exactly G of x. So why, in fact, I spent so much time, in fact, to define you, in fact, the Gaussian distribution, because here you know, I think all of you, that's okay, HMC, you need somehow to define a Gaussian distribution, right? Here, you in fact, in HMC, you consider, in fact, the Gaussian distribution on the cotangent space of RD, which is simply with the canonical metric, the standard Gaussian distribution for any points. But here, if you now have a metric, okay, so here, in fact, at a point x, the distribution which I will consider for my momentum, okay, in the metric case, is this Gaussian distribution with a covariance matrix, which is G of x. Yeah. So that was for a given point x. Now, if you want to handle with the whole cotangent bundle, okay, the cotangent bundle is just a union across all the elements of my manifold of, okay, this cotangent space at given point x. Okay. So now, okay, if you know a bit of differential geometry, so here now you know that's okay. The cotangent bundle is itself a manifold, yeah, and based on the metric on M, you can define a metric on this cotangent bundle, which I denote by G star this time. So I will not give you, in fact, somehow the construction and the expression of this particular metric. Okay, we don't really care. Okay, at least for me, for the moment. So here, what is important, in fact, in all this construction is that, okay, if what is important is based on the metric G on the manifold, you can define the Riemannian form or the Riemannian measure on my manifold, okay, which plays the role of the Lebesgue measure on RD, and in local charts, this Riemannian measures take the form of, in fact, the square root of the determinant of my metric dx, the Lebesgue measure. So here, in fact, really the expression is local charts. Okay. But and here, in fact, what is quite interesting with the matrix G star that you can define on my cotangent bundle is that now, if you consider, in fact, the Riemannian measure on my cotangent bundle associated with my new metric G star, okay, it is exactly in the local charts, just the Lebesgue measure. Okay. So here, in fact, the important information is that somehow, okay, you can, based on the Riemannian manifold, okay, on the cotangent bundle, okay, you can define a measure which somehow, in fact, is local chart, just is the Lebesgue measure. Okay. Yes. No. And no. Otherwise, in fact, you would not have this. That's a good question. No, in fact, because here you are independent. So here it's not, yeah. So yes, so it took me 1 year to understand this. So if you have any questions. Okay. So yeah, so that's in fact a 1 year summary of what we try to study. In fact, in some book of Lee and a mysterious paper by Mock, which in fact is the paper which introduced formally, in fact, this metric G star in such a way that, okay, you can have, in a local charts, you have the Lebesgue measure on the cotangent bundle. Okay. And so here, okay, now, here you, if you knows well the HMC, you want now to define the Hamiltonian function on my cotangent bundle in such a way that the the marginal distribution of my density is exactly right. Is exactly the my target distribution. Okay. And so to this end, okay, so here, in fact, since in fact pi has density exponential minus v with respect to the Lebesgue measure, okay. So here, in fact, with respect to the Riemannian measure on M, it has a density, okay. Just I multiply and divide by the square root of the determinant of G, and in fact, the density of pi with respect to the volume measure on M is in fact proportional to exponential minus v minus 1/2 log depth of G of x. Okay. And what is in fact what you get is so here in fact is the density that now you want to handle, and the corresponding in fact Hamiltonian function that you need to consider h of x and p is, as in the traditional HMC, this density plus okay the log depth, the log of the density of the Gaussian measure at the cotangent model at my given point x, which is exactly the norm square of p g of x minus 1. Okay. So here, okay, here is in fact the extension of Hamiltonian function on manifold with a metric, okay, given by G, okay, in the case where you have exactly this form for the target density. Okay. And here is some so the extension. So here, in fact, if you would not have in fact these terms there if you would specify directly the density of the target distribution with respect to the Riemannian volume. But here, in fact, in application, you don't have such a form. Okay, you just have that, in fact, your density is defined just on a constraint space, and that's it with respect to the Lebesgue measure, and that's all you care. Here, since in fact you want to put some metric, okay, which is not the canonical metric, you end up with in fact an extra term, okay, in your density, if you want to consider the Hamiltonian function associated with this metric. Okay. So now, okay, based on this Hamiltonian function, okay, you can define the extended targets, okay, exactly as in the traditional HMC. So here, in fact, this extended target pi bar here will have density with respect to the Riemannian measure here, which is proportional to exponential minus h. So here, okay, nothing fancy. Okay, you just have okay a way to extend the extended targets distribution, which is a good name for it. And so, in particular, in the case where you consider the canonical metric, okay, a sanity check said to you that it's a usual extended target distribution on R2D. So now the goal, okay, if you want to extend the HMC in this case, you would like, in fact, an algorithm, an MCMC algorithm, which, in fact, aim to sample from this target distribution. Okay. And in particular, okay, you want to, again, extend HMC. So you would like, in fact, to use Hamiltonian dynamics associated with this HMC Hamiltonian function. So here I just call you, in fact, the Hamiltonian dynamics associated with H. So you just say just the dynamic with respect to the position and momentum, x dots and p dots. So that the derivative with respect to time of the position is okay. The derivative with respect to the momentum of the Hamiltonian function, and okay, vice versa for the momentum. Here you just add the minus. Okay. And here, okay, it's a bit more complicated, of course. In particular, now if you write the Hamiltonian dynamics associated with the Hamiltonian function I just defined you before. So here, in fact, you end up with the equation, the differential equation satisfied by the position, make, in fact, enter now the metric. g of x minus 1 times p. Whereas, in fact, for the momentum, it is not that bad, okay, because here you have still, in fact, just a function of the position. Whereas, in fact, here, in fact, the main difficulty will be somehow there, because now compared to traditional Euclidean HMC, where you just have the momentum now, with differential dynamics associated with the position, you have, in fact, a nonlinear function of the position and the momentum. Okay. So now for a given metric, I will not specify this metric. So here, in fact, the Riemann HMC, which has been suggested by Oliviero-Dumus and M.Carl, meaning that, in fact, here you will successively use a splitting algorithm, which, in fact, will try, in fact, to solve the Hamiltonian dynamics with case steps, and you will correct your proposal as, in fact, the usual astigmatic-Metropolis ratio. And here, in fact, you can really see that it's basically the HMC algorithms. In fact, all is hidden in the numerical integration of the Hamiltonian dynamics on your manifold with your particular metric. Okay, so, and here, in fact, in their paper, they just rely on well-known numerical analysis to suggest some algorithm to solve this Hamiltonian dynamics in such a way that, in fact, this proposal stay reversible. And that's all the trick in HMC. If you, in fact, your discretization is reversible and symplectic, you can still, in fact, use the same recipes as HMC. And here is some results. Okay, so here it seems to behave much better. But now, okay, we want, in fact, to try to extend this algorithm and this idea in the case where you really have a geometric constraints. Okay, so here in their paper, they just handle mainly, in fact, RD. And what we really want to achieve is that, in fact, in the solution proposed by Jeremy and M.Carl, in fact, somehow it's an ideal situation, okay, because, and even in traditional numerical analysis, what you suppose is that when you will solve the Hamiltonian dynamics, but I will go back to it later, but when you try to solve nonlinear Hamiltonian dynamics, you will use, in fact, implicit method, and fundamentally, this implicit method will not be reversible, except that, in fact, you suppose that you have a unique solution to this fixed point equation. In general, in fact, you don't have any you don't have unicity for this fixed point equation, and in fact, you need to have extra condition to end up with algorithm which is reversible. And what we try, in fact, to handle is that, okay, can we, in fact, try to design some metric G and which can handle some particular constraint in such a way that we can, in fact, really have numerical MCMC algorithm using numerical recipe for the Hamiltonian dynamics, for which the overall algorithm is still reversible. So in fact, to construct the metrics that we want to handle, okay, here we will go to optimization theory. Okay, so here I will in fact focus now on a set of constraints which is convex, okay, because in this particular case, you can define quite canonical way, let's say, what is called a self-concordant barrier metric, which is based on a function with phi here, which is called self-concordance, in such a way that, in fact, it will play a role of a barrier for your constraints. So here I said that phi is a self-concordant barrier associated with my constraints u. Okay, so for the moment, don't look at the condition mu there. Okay, it's a technical condition. Here, what is important is that, okay, phi is somehow smooth. Okay, it's C3 on u. Phi is convex, and okay, this function phi will explode at the boundary of your constraints. And here I will not show to you the very technical condition on the second and the third derivative of this function, okay? Because in fact, so I will spend half an hour to explain this condition. So here, basically, this condition says that roughly the second derivative of phi is locally 2 Lipschitz, okay? And phi also is locally mu Lipschitz. Okay. So now, based on this, in fact, concordant, self-concordant function, a natural metric on my convex sets U, okay, if I now have such a self-concordant function, the natural metric G is, in fact, the Hessian of phi. Okay. So here, now, okay, so to be, in fact, a metric, of course, in fact, is suppose somehow that in fact phi is not convex, it is strictly convex, okay, so in such a way that in fact you have positive definite for any function, for any element of your constraint space. But that's it defines perfectly in fact a metric on my convex set M. So now in fact this question is a converse. If you have a convex set, can you build in fact such a self-concordant function? And turns out yes, you can. In fact, for any convex set M, you can design a self-concordant barrier. Okay, you don't have, in fact, an explicit expression for it. Okay, but okay, nevertheless, you know that it exists. Now, okay, let's now assume that okay, your constraint is convex. Okay, it's a huge supposition, but still okay. It's you need to begin with something now, and I will assume that I have access to some self-concordant function in such a way that I can define my metric G. Okay, and under this framework, okay, can now in fact design an HMC algorithm, okay, for which in fact phi is really reversible. Just to a bit of a literature, okay, review. So here, in fact, the norm. So here you can define, in fact, indirectly the manifold, the norm associated with respect to g of x. Okay. So here you just, in fact, define what it makes sense. Okay, I define you, in fact, the metric g of x here on the tangent model, but in fact, you can also define it directly because you have a subset of RD. You can define for any y, okay, g of x is the same. Okay, you just have that's this g of x, y, y. And it turns out that okay, using in fact this family of norm, okay, so it define, okay, if you consider now the ball associated with this family of norm, okay, it has been called, in fact, thinking ellipsoid, and it plays a big role, in fact, in the some analysis in a convex optimization. So in particular, okay, here, what you in the case where M is just some inequality constraints of the form A of x smaller than B, where in fact you meet such a constraint a lot for in statistics or operation research task. Here, a natural new self-concordant function is given by what is called logarithm barrier. Phi of x is equals to the opposite of the sum from I to M of the log of pi minus AI transpose x. So here, in fact, you can check, okay, it has been done by Nesterov and Nemirovsky in one of their papers, that in fact this function define appropriate self-concordant function on my set of inequality constraints. Okay, so here is some example, in fact, of a constraint state, and here, in fact, I just plot for some given points, given points here, here, and here, some linking ellipsoid. So here, what's in fact for a given radius, and what you can in fact what you can check is that in fact every Dinkin ellipsoid lies into your constraints. Okay? Compared to if you would have considered, in fact, Euclidean ball. Okay, you will be out your constraints, whereas in fact here, using Dynkin ellipsoid, in fact, are always defined in all lies in your manifold. So now, in fact, based on this observation, one algorithm, one MCMT algorithm, which has been suggested, is called the Dynkin walk, which in fact just consists in at a given point, you consider the Dynkin ball at the given point, and you sample uniformly in this Dynkin wall, in this Dynkin ellipsoid. So that's the a valid MCMC, which is called Dynkin walk, and it has been analyzed in a paper by Cannon and Narayanan. Another algorithm, which is named the geodesic walls, just consists in fact in considering the geodesic associated with the metric that you put on your manifold. Okay, but in this case, okay, you should have exactly the geodesic associated on your manifold, which is in general not the case. And here, okay, it's more related of what we have suggested. So here in a paper by Lee and Van Pala, consider in fact the Riemannian HMC algorithm, where okay, here it's you suppose that you can exactly compute the Hamiltonian dynamics associated with your metric. Okay, that I just give you before. They don't consider any numerical scheme. And then a paper last year by Cook and co-author consider in fact the Girolami-Calder head kind of algorithm for discretizing the randomized HMs, meaning that in fact they consider okay, numerical scheme to discretize the Hamiltonian dynamics on your manifold, but still, in fact, they assume implicitly that you just have one solution for the fixed point equation, which you use to discretize your Hamiltonian dynamics, your nonlinear Hamiltonian dynamics. Okay, and so here, in fact, so here, as I wrote, Maxence wrote, not me, but wrote that the experiment highlights asymptotic bias. Okay, so in fact, I would say that in fact the experiment hide the asymptotic bias. That in fact they don't really they just plot some autocorrelation time, as in fact Calder head and Girolami, whereas in fact and that's what I will illustrate later, that in fact in their algorithm you have in fact a numerical bias, which comes from the fact that the numerical algorithms that they use in general do not have a unique solution. Okay, and in fact from this, in fact it has been known that if you use such a method not in without any adjustments, you will end up with asymptotic bias. Okay, and that's what we want to handle in this paper. Okay, and for this, okay, we'll take a look on numerical analysis. Okay, and numerical paper for MCMC in particular. Okay, we look at a paper by Zappa and co-author, which in fact handles this main problem, but in a, let's say, simpler situation, where in fact what you want to adapt, if you would like in fact to adapt the usual random walk metropolis on a constraint space. Okay, and in this particular situation, it is not that simple, because in fact, if you use the usual random walk metropolis on a constraint space, you can in fact go out your constraint space. Okay, and you cannot simply project, okay, on your constraint space. Otherwise, in fact, you end up with some asymptotic bias. And what's in fact Zappa and co-author suggest is in fact a particular projection, which is not in fact which will not be in fact the usual projection of convex space if the constraint space is convex. It's a bit more subtle. And in fact, even using in fact this particular projection, you need to add a step in your metropolis hasting algorithm, meaning that if you now, okay, you will propose a move based on your projection, and you need to check that now if you start your algorithm again, okay, from your proposition, you go back to your initial state. Just preserve the reversibility of a proposal. So I will be a bit more precise later on, okay, but to say that, in fact, Zappa et al. Was a big source of inspiration for us. So here is just a summary of what we will. I will give you some details now later. Is that okay? I want to adapt HMC to a constraints manifold with a particular metric. In particular, I assume that M is a convex set with a self-concordant barrier. And okay, I want somehow to end up with an algorithm which solves the problem of Cook and co-author, meaning that I want to erase the bias of their method and handle that okay, your numerical recipe can have multiple solutions. So here, okay, I will skip this because I don't think it's quite, it's not give you that, it does not give you in fact the main idea. It's just technical. And here, okay, I will just enter into the details on our algorithm. So here I will in fact first present you the numerical algorithm that we use to solve the nonlinear Hamiltonian dynamics, and then okay, I will give you some details about in fact try to fix the problem that you can have multiple solutions. So here, as I said to you, okay, I was quite brief, but in fact, when you handle with nonlinear Hamiltonian, okay, you use splitting algorithm, meaning that okay, here I will write my Hamiltonian function as the sum of two functions h1 and h2, where okay, h1 is the simple part, okay, as I already mentioned, meaning that here is just a function of x and you don't have a position. So here, since you just depend on x, the Hamiltonian dynamics associated with this particular Hamiltonian function can be solved. Okay, it's quite explicit, it's completely explicit, right? And it just, okay, for a time step h over 2, a solution is just given by, okay, you follow, in fact, just you fixed x and p, okay, x and p is fixed, it's your initial point, and you just add, choose the momentum minus h over 2, the partial derivative with respect to is of h1, okay? But okay, here's the burden, okay, when you want to implement things, and I will go it later, is that okay, you need to somehow derive this function, and okay, it can be quite a mess. Let's assume that you can do it. Yeah. Now, okay, integrating the Hamiltonian dynamics associated with this function can be done. And now, okay, it will be fast. So now, okay, I can now handle the integration of the second part of my Hamiltonian function. For this, I will use what is called the generalized big frog, okay, scheme. It consists, in fact, for a step size h it consists in trying to find fixed points of this particular equation. So here's my fixed point, because I try to look at P1 alpha and P1 and X1, which satisfies this system of equation. And here, in fact, it's exactly a fixed point problem. Okay. And here, okay, I will assume that this problem, in fact, you can check that for the particular metric that we handle, this particular problem has always a solution, okay, for h small enough. And I will denote by f of h the set of solution of this particular problem. So here it's still, let's say, yeah, ideal, meaning that I assume that I can have access to all the solutions of my fixed points problem, okay, but it's a bit, I would say, a bit more general, that's a bit more realistic, not completely realistic, but a bit more realistic that's Cook and co-author, meaning that, okay, here I can handle the fact that I can have multiple solutions. Okay, now I have f of h, and what I will assume, in fact, on f of h, that's almost an evolution, meaning that, okay, if I see it as a set value map, the composition of the function by itself, in fact, applied to z, I ask that z belongs, in fact, to the composition of this function. Okay. And in fact, you can exactly check it for, as I said, on the for self-concordant function. And you know that it's always an empty if h is small enough, depending on the current state. Okay, so now in fact the complete algorithm to solve my Hamiltonian dynamics will be in fact the composition of the operator and the operation I just presented you before. In fact, you have a reversible scheme. Okay, I will first solve with the time step h/2 the Hamiltonian dynamics with respect to h2. I will, in fact, now solve the dynamics with respect to h1, and again the dynamic with respect to h2. And don't look at the function s. Okay, it's just not very important. Okay. So here, in fact, now you end up with, in fact, you end up with almost, in fact, a reversible map, right? But okay. Now, in practice, you cannot have access exactly to the set of solution. It's not very realistic. What you just have is some kind of numerical recipe. And here I will denote my numerical recipe phi of h. Okay. Whatever numerical recipe you can use, okay, to solve this fixed point equation. So you could use Newton, okay, as in the paper by Zappa and Coulter. Or in our paper, we just use a fixed point solver, okay, that's fancy. And here, in fact, what is implemented in practice, okay, it's in fact this discretization of the Hamiltonian dynamics, where, okay, here you can always solve, in fact, the Hamiltonian dynamics associated with H2 is not, it's straightforward, but here, okay, you use your numerical recipe to try to solve the Hamiltonian dynamics with respect to H1, which is nonlinear. Okay? So that's, in fact, you end up with two somehow discretization of the Hamiltonian dynamics, one which is a bit more realistic, and this one which is completely realistic. Okay, and what you would like, okay, is can we in fact try to analyze and check that the HMC algorithm, okay, is indeed reversible with respect to the extended targets. If you use, okay, these two kind of discretization of your Hamiltonian dynamics. It turns out, in fact, and it's related to the paper by Zappa, that in fact, you cannot directly use this discretization. You need to check that, in fact, if given your proposal, so here Z1, okay, so here Z1 is the set which is given by my numerical recipe for the fixed point problem associated with the Hamiltonian dynamics of H1. I need to check that given Z1, okay, if I follow my numerical discretization, my numerical solution for my fixed point equation, I can go back to Z0. Okay? And in fact, but in practice, okay, you will never go back to your initial point, okay? It's not credible. And here, in fact, you need to, in fact, consider some kind of tolerance, okay, to check that, okay, here you tolerate, in fact, that you will go back up to some parameter eta to your initial point. And to measure, in fact, your error, you will consider, in fact, the Deakin norm, okay, at my given point Z0. Okay, and I will try to explain to you why, in fact, it's important to consider such a norm, okay, because, in fact, it is designed to handle the variation of your proposal based on the scaling of the Hamiltonian dynamics. Okay, so here, okay, and so here I write to you for the numerical recipe phi of H, but okay, it's also holds for the if you can have access to exactly the fixed point solution of your fixed point equation. So, okay, so here I will not have the time to justify properly, okay, but I will be very quick. So, in fact, why, in fact, it's important to consider this weighting norm, okay, to see if I move or not. So here, in fact, if I consider this weighting norm, the difference between my proposal, if I follow phi of h minus my initial points, okay, it's approximately, in fact, h times the norm of x dot g of x plus h p dot g of x minus 1, okay? And in fact, close to the boundary, okay, here what is quite a nightmare is that, in fact, based on the dynamics that you want to discretize, you end up that, in fact, if you consider just only the norm of x dot and p dot, in fact, at the boundary, the norm of the Euclidean norm of x dot is almost 0, in fact, and the norm of p dot, in fact, goes to infinity. Okay. So, in fact, in a physical sense, what does, in fact, when you look at, in fact, the geodesic associated with the self-concordant barrier, you can see that, in fact, it decelerates a lot close to the barrier. So, in fact, it prevents the algorithm to, in fact, cross the barrier by decelerating, in fact, a lot your dynamics. Okay, so here, in fact, I will just end up with some theoretical results. So here, in fact, what's the end up of the story is that, in fact, if you consider, in fact, self-concordant barrier, which is also what we call alpha regular, okay, we can check that, in fact, if the step size is small enough, okay, so here you need to check somehow that the step size is each time smaller than a given quantity which depends on your current time, but which is completely explicit. Then, okay, the summary of our result is that, okay, the algorithm is indeed reversible. Okay, so I will not enter into the detail, and just I want to conclude quickly on the simulation part. Okay, so here, what I want to consider some truncated Gaussian, okay, case, just for a sanity check. And I will consider M, which is the hypercube or the simplex, and for d equals 5 or 10, okay, not that's big, okay, because we somehow need a ground truth, okay, to check our algorithm. In fact, the problem to sample on a constraint set is very, very complicated at some point, and to have a reliable result is not that simple. And here, okay, so here are the target density I want. Okay, here's the quantity which I want to approximate is the integral of my constraint state of the scalar product of x with respect to mu, where mu is the mean of my Gaussian distribution. Okay. And here are the results. So here you can clearly see, in fact, the bias associated with the randomized HMC, where you don't include any reversible check. Okay. Here are our solution, and here, okay, what we think to be the ground truth, where in fact we use Mala with a lot of iteration, and for a comparison. And here for the dimension 5 and dimension 10, for the case of M is just the hypercube, and for the case of the simplex, okay, we use the independence metropolis testing to have a ground truth. And here are the results. Again, okay, you can see that you have, in fact, a bias for a competitor. Whereas, okay, here we still have a bias. I will not lie to you, because in fact, you have, in fact, a tolerance.
From the slide.
Sorry, on.
Yeah,
but here, in fact, you would still have a tolerance. In fact, you have a tolerance parameter in checking that you go back, in fact, to your initial point. But that's live. You cannot make it easier, in fact. But here, in fact, it's somehow a compromise about the accuracy that you want. You can control, in fact, the bias by the tolerance. Okay, if you have a large amount of computational resources, okay, you can take a very, very small tolerance parameter. Okay, and then, okay, the bias will be diminished. But otherwise, if you have less computing resources, in fact, you need to take, of course, a tolerance parameter, which is large, okay, and you will end up with unbiased. Okay, so that's, in fact, the somehow the conclusion of all this paper. Okay, and thank you very much for your attention.